billion kilometers away, a feat of engineering and perseverance that defies belief. The fact that Voyager 1 still communicates with Earth using only 23 W of power less than that used by a common light bulb, and has just 69 kilobs of onboard memory, yet continues to function, is nothing short of miraculous. These aging yet resilient machines are not merely drifting through the cosmos. They are still performing science, capturing data that challenges our understanding of the universe. This all began with a visionary plan hatched by NASA's Jet Propulsion Laboratory scientist Gary Flandro, who used nothing but a pencil and his analytical mind to recognize a once-in 176 years opportunity. In the late 1970s and early 1980s, the four outer gas giants, Jupiter, Saturn, Uranus, and Neptune, would align in such a way that a spacecraft could slingshot between them, gaining momentum from each planet's gravity in a precise cosmic choreography. This planetary alignment formed a kind of celestial necklace, creating an efficient route that would drastically reduce travel time to Neptune from 30 years to just 12. Recognizing that such an alignment would not occur again for over a century, NASA moved quickly, launching two nearly identical probes, Voyager 1 and Voyager 2, just 15 days apart during the summer of 1977. What followed was a mission that would shatter all expectations and become one of the most profound achievements in the history of space exploration. The Voyagers were originally tasked with a close-up tour of the outer planets, a mission that yielded unprecedented discoveries. Voyager 1 flew past Jupiter and Saturn, revealing the gas giants' turbulent atmospheres and the complex, dynamic nature of their moons. Among the most significant findings was the detection of active volcanoes on Jupiter's moon Io and the realization that Saturn's moon Titan might harbor an atmosphere thicker than Earth's. Voyager 2, traveling on a different trajectory, achieved its own historic milestones by becoming the only spacecraft to visit Uranus in 1986 and Neptune in 1989. The images and data it returned forever changed humanity's perception of these distant icy worlds. These encounters revealed magnetic fields, unexpected weather patterns, and rings around planets previously thought to lack them. Voyager 2's passage through the outer solar system showed us not dead frozen orbs, but vibrant, active worlds. Though their original planetary missions ended in the 1980s, the Voyagers pressed on. Their next destination wasn't a planet, but the great unknown beyond the reach of the Sun's protective bubble, the interstellar medium. As they traveled farther from the Sun, they continued to collect data on the solar wind, cosmic rays, and magnetic fields, transmitting their findings back to Earth using giant 12-m-wide satellite dishes and a radio communication system that operated at the speed of light but faced a growing delay. Now over 20 hours for signals to make the round trip. The data sent back is stored on old-fashioned 8-track tape recorders before being beamed home through the Deep Space Network. Despite the limitations of 1970s technology, the Voyager's design has proven remarkably robust. These spacecraft are no larger than a Volkswagen Beetle and operate autonomously using primitive software and backup systems engineered in an era long before smartphones or high-speed internet. Their trajectory to Jupiter alone took them 10 times the distance from Earth to Mercury and required navigating through the asteroid belt, a hazardous region once feared impassable. The success of these missions, following in the footsteps of Pioneer 10 and 11, proved otherwise. Along the way, Voyager 1 and 2 also contributed to our understanding of the heliosphere, the vast bubble-like region of space dominated by the solar wind and magnetic field of the Sun. The edge of this bubble, the heliopause, marks the beginning of interstellar space and became a prime target for NASA's extended Voyager mission. For years, scientists closely monitored the data coming from the probes, hoping to pinpoint the exact moment they would cross this boundary. Voyager 1 reached the heliopause on August 25, 2012, at a distance of about 121 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. Surprisingly, the crossing was not immediately obvious. Unlike predictions that envisioned a sudden shift in magnetic field direction, Voyager 1 instead recorded a significant jump in plasma density, evidence that it had entered a region where the solar wind no longer dominated. Yet the magnetic field direction remained surprisingly consistent. leading to some confusion among scientists. It was later understood that the transition was more complex than previously thought, and that the heliopause is not a sharp boundary, but a diffuse and turbulent frontier. The spacecraft had entered interstellar space, where the environment is shaped not by our sun, but by the collective influence of distant stars, supernovae, and galactic forces. Voyager 2, following a slower path, eventually crossed the heliopause as well on November 5, 2018. Like its twin, it confirmed an increase in plasma density, validating the earlier findings of Voyager 1 and proving that both probes had indeed left the solar bubble. These transitions marked the first time humanity had physically crossed into the interstellar medium, providing in situ data that had never before been accessible. The discoveries were invaluable, not only confirming models of the solar system's boundaries, but offering clues about how our local stellar neighborhood interacts with the broader galaxy. Beyond the heliopause lies the vast and mysterious Oort cloud, a hypothetical shell of icy bodies that surrounds the solar system and may contain the building blocks of comets. While it will take thousands of years for either Voyager to reach the inner edge of the Oort cloud, their current trajectories point them ever outward toward the stars. The ongoing operation of the Voyager spacecraft is a testament to human ingenuity and scientific ambition. Each day, these tiny probes communicate from a place no human will likely reach in our lifetimes, sending back data that challenges and refines our understanding of space, magnetism, plasma physics, and more. Their continued health and ability to transmit signals from such a great distance require careful management of dwindling power supplies and the aging of onboard systems. Engineers have turned off non-essential instruments to conserve energy and stretch the mission as long as possible, aiming to keep at least some instruments functioning into the early 2030s. These decisions are often difficult, like choosing which scientific instrument to shut down next, but are necessary to extend the lives of these unprecedented explorers. In addition to their scientific legacy, the Voyagers carry a symbolic message from Earth, the Golden Records. These phonograph records, mounted on each spacecraft, contain sounds and images meant to convey the diversity of life and culture on our planet to any extraterrestrial intelligence that might one day find them. They include greetings in 55 languages, ranging from bark to Chuck Berry, and a diagram of the solar system with the spacecraft's trajectory. These records reflect not only our curiosity, but our hope that we are not alone, and that someone, somewhere, might one day receive our message. The Voyager missions are not just scientific endeavors. They are humanity's message in a bottle drifting in the cosmic ocean. They remind us of what we can achieve with determination, creativity, and a sense of wonder. Despite being launched nearly 5 decades ago, these spacecraft continue to defy time and distance, rewriting textbooks and captivating imaginations. Their journey is far from over. Even if one day their voices fall silent, long after their power fades, Voyager 1 and 2 will continue traveling through the galaxy, silent witnesses to the story of a small blue planet that dared to reach for the stars. The continued survival of the Voyager spacecraft is not only a feat of engineering, but also a reminder of the profound impact that careful planning and visionary science can have over generations. Both probes have outlived nearly all the people and technologies that created them, operating in a realm where no spacecraft has ever gone, and doing so with systems that would be considered prehistoric by today's standards. Engineers at NASA have worked tirelessly to keep the probes functioning, often finding creative workarounds for problems that arise from the inevitable wear and tear of time. They've reprogrammed software remotely, rerouted circuits, and carefully managed the decay of the spacecraft's power sources, plutonium-238 radioisotope thermoelectric generators that gradually produce less energy with each passing year. As this power dwindles, scientists must make increasingly difficult decisions about which instruments to keep running and which to shut down. These decisions are made not only with scientific goals in mind, but also with the reverence and awe that come with working on one of humanity's greatest exploratory missions. Each byte of data returned by Voyager is hard-won and immensely valuable. The information it provides about cosmic rays, magnetic fields, and plasma waves offers rare insights into the nature of interstellar space. These measurements help scientists model how our solar system interacts with the rest of the galaxy, shedding light on the shape and behavior of the heliosphere, the invisible protective bubble that shields life on Earth from harmful galactic radiation. Before Voyager, this region was purely theoretical. No spacecraft had ever ventured that far or attempted to study it in such detail. Now, thanks to these twin emissaries, we have a clearer understanding of how the sun's influence wanes in the face of the interstellar environment, and how our solar system fits into the broader context of the Milky Way. Among the most intriguing discoveries made by the Voyager probes after crossing the heliopause was the surprising uniformity of the magnetic field. Contrary to expectations that it would shift drastically beyond the solar boundary, the field remained largely consistent, indicating that the boundary is not as sharply defined as once thought. This suggests a more complex interaction between the solar wind and interstellar medium than models previously accounted for. Moreover, the increased plasma density detected by Voyager 1 gave researchers their first direct measurement of interstellar plasma, a milestone achievement that took over 4 decades to accomplish. It confirmed that the spacecraft had indeed left the sun's direct domain and entered a region dominated by distant stars, supernova remnants, and ancient diffused matter scattered across the galaxy. The Voyager's continued journey has not only advanced science, but also captured the imagination of people worldwide. These tiny, distant travelers embody the spirit of discovery and the innate human desire to explore the unknown. With each new milestone, they remind us of the vastness of the universe and the limits of our understanding. The fact that a machine launched in the 1970s, operated by commands that can take over 20 hours to reach it, can still teach us something new is a testament to human perseverance and curiosity. Scientists and engineers refer to the Voyagers with a kind of affection usually reserved for old friends or wise elders. They are, in a sense, elder statesmen of the space age, silent, steady, and filled with secrets from the depths of the cosmos. As they drift farther into space, they approach the realm of the Oort cloud, the vast spherical shell of icy bodies that